Welcome to our demo of AI/ML on OpenShift. We'll be showing you how OpenShift as a platform provides the capability to address a large portion of the challenges that are prevalent in managing and moving workloads at all stages of the AI/ML workflow. We're going to take a credit card fraud detection use case as an example, but really most of this demo could apply to any AI/ML workflow. So this slide shows the end-to-end process and describes challenges that are typically experienced by four different personas: data engineers, data scientists, application developers, and IT operations in the end-to-end AI/ML implementation flow. Due to the nature of this flow, it's not possible to solve these challenges in isolation. Data engineers need to acquire, duplicate, split, merge, combine, architect, and prepare data for later consumption by the data scientist, who clearly needs to train the model. They also need to experiment and undertake a good degree of trial and error. And they also need to work closely with application developers, who need to ensure seamless and effective integration of models with intelligent applications. And finally, IT operations need to deal with data, application and infrastructure security, performance, infrastructure management, and ensure that all tools that are used across the chain, they're supportable and they're well functioning. So as we go through our demo today, we'll be showing how our platform OpenShift addresses the challenges and the pain points that you can see here that these folks encounter. So this is the flow of our demo, this credit card fraud detection workflow. You can see the same four actors that we just mentioned: the data engineer, the data scientist, the IT developer, and IT operations. So to the flow of the demo. Credit card transactions are sent in from e-commerce sites and from merchants into OpenShift's payment service. And each transaction is routed both to the left into our Kafka streaming service and also to the right to our fraud detection service. So first, transactions are piped through the streaming service. And the work of our first actor, the data engineer, begins. The data engineer is responsible for cleaning data and making it consumable later on by the data scientist. They utilize Jupyter Notebooks and Spark, the big data management tool, to combine this streaming data from Kafka with static data from this PostgreSQL database. And they push that cleansed data into an object store. This S3 store, which acts as a very effective workflow, both sharing and handoff mechanism between the data engineer and the data scientist, addressing a huge problem in AI/ML, which is collaboration between potentially siloed parties. Next, we enter the data scientist, who pulls the data cleansed by the data engineer and trains the model and utilize various visualization tools, including TensorBoard, facilitated by the OpenShift platform. Next, we utilize a sampling of OpenShift's ML Ops capability to apply quality assurance, security, as well as speed and automation to the process of moving that model from the data scientist laptop right through to production. And then at runtime, as we mentioned a moment ago, each credit card transaction hits our fraud detection service, where a call is made to a runtime model serving component. This is effectively the inferencing stage, which can be TensorFlow serving or Selden, from which a probability of fraud associated with this particular transaction is returned back to the fraud detection service, and appropriate action can be taken. So that's a quick overview of the demo. So what we're going to do now is we're going to split our demo down into smaller parts and show how OpenShift addresses challenges that are experienced by particular personas or actors in that part of the demo, as well as how we're assisting IT ops down here, who touch all stages of the demo. So first, the data engineer and preparation and cleansing of the data for later consumption by the data scientist. What kind of challenges and requirements do I, as a data engineer, face? First off, I need a self-service platform where I can provision the tools that I want, things like Spark and Jupyter Hub, where I can combine this streaming credit card data with static relational data in my database here. I need tools enabling me to produce high quality data for the data scientist, because high quality data is required for high quality models. I want to be able to provision these tools on demand when I need them, independent of IT, without tickets or wait times. I don't want to compete for this Spark cluster with other data engineers, which would slow me down. Second, as a data engineer, I want a workflow driven approach where I can easily hand off what I produce to the consumer of the data scientist. One such handover mechanism, as we've just mentioned, that easily facilitates the sharing of work is using object storage like an S3 bucket here. So let's switch across to our browser, across to OpenShift. And over here you can see that I'm logged in as a user called Data Engineer. We're now going to demonstrate self-service by the data engineer of the tools that they need. The primary vehicle through which self-service is achieved on OpenShift is this Operator Hub, which is a catalog containing over 400 self-service tools for data engineers as well as data scientists and application developers. Let's highlight one such tool set, which is the Open Data Hub Operator. So this is the Open Data Hub Operator, which is effectively a menu of AI/ML tools that also acts as a reference architecture for AI/ML on OpenShift. You can see we've already installed the Open Data Hub Operator. And because we've already installed the Open Data Hub Operator, OpenShift and the operator creates these routes or URLs into my chosen tools within the Open Data Hub. Things like Jupyter Hub, Spark, TensorBoard, etc. So let's drill into Jupyter Hub, where the data engineer is going to do their work. The first thing that they are prompted for are their OpenShift credentials. And in the process, what OpenShift is going to do is implement role-based access control. In other words, this data engineer won't be able to see or access anything that they're not allowed to. And now you can see on this spawning page more self-service options. First, the image to work with. It's very easy for the OpenShift administrator to create an image containing any combinations of tools that OpenShift users can work with. As I'm a data engineer at this point, I'm going to work with this Spark Hadoop based image. Later on, the data scientists will work with this Keras TensorFlow Panda based image. These are just a sampling of tools. Any combination of desired tools and their versions can be created upfront and made available for self-service, speeding up everybody's work and eliminating problems with different versions of tools across the organization. And of course, with OpenShift, we're not opinionated or restrictive in the tools that you can use. You can use any tools that you desire. The second self-service item here that you can see on this page is the amount of resources, CPU and memory, to allocate to this job. OpenShift enables the creation of prepackaged bundle sizes like these. I'm going to choose a large one for my resource-hungry Spark cluster. When I'm finished, this CPU and memory is going to be returned back to the available resources for everybody else. So it's a highly efficient and streamlined use of our resources, which is a big win for IT operations. And third self-service item here, I can select how many GPUs that I want allocated to this Jupyter Notebook run. And again, they're also returned back to the pool when I'm finished. So to save time, I've already logged in and ran my Jupyter Notebook here. I've since disconnected, as you can see. This is the actual Jupyter Notebook used by the data engineer. A Jupyter Notebook is a mostly Python-based coding environment that's split down into cells, as you can see here. And each cell can be run individually, or the entire notebook consisting of all cells can be run at once. A cell can display formatted text or code, as well as charts and diagrams. So yeah, this kind of option to run all at once or individual cells suits the experimental iterative nature of the work that's done by data scientists and data engineers. So like I said, I ran this one previously to save time, so I'm going to walk through it pretty quickly, because really of most importance and what we're mostly trying to highlight here is not the code, but rather just really the capability. So you can see initially I set up some environment variables like the address of my object storage here. Then I connect to my Spark cluster, pull in data from my relational database, pull in data from my Kafka, the streaming credit card data, and I join those data together. And what I do then is I push those to my object store to a location labeled credit card clean CSV. So a couple of points I'd like to highlight here. First, this is the Spark cluster here that's exclusively for this data engineer. Again, no contention or competition for a scarce Spark cluster, as is often the case with data platform like OpenShift. Second thing I want to point out is this is our S3 object store and the cleansed data that the data engineer just pushed to it here under the credit card clean CSV location. Again, highlighting this effective workflow driven approach to handing off data and work from one actor to the next, in this case from the data engineer to the data scientist. So that's really the data engineer part of the demo. So let's move on now with our demo. The next part of our demo, we're going to focus on the data scientist. So as a data scientist, what pain points does OpenShift alleviate, enabling me to do my job more effectively and more efficiently? Some of these are quite similar to the requirements of the data engineer that you just saw. First off, I want a self-service platform where I'm independent of IT without tickets or wait times, where I can provision a varied and rich set of tools for model training and model visualization, assisting me as I train and experiment. Not only to train the model once, but to constantly retrain models, addressing the model drift that's an inherent part of AI/ML, because the data that's relevant to train the model today is different to the data that will be needed next year. So just look at the effect of COVID on, say for example, aviation traffic models. Second, as a data engineer, I want a set of tools that make it easy for me to hand off my work for model validation and model consumption by application development. So now we're going to briefly showcase a sampling of the data science focused tools and tasks that OpenShift facilitates. So I'm going to switch across to a different browser, and you can see this time I'm logged in as a user called Data Scientist. This time I'm going to choose, or I did choose, a smaller sampling of tools from the Open Data Hub. I'm mainly interested in Jupyter Hub. At this point, as a data scientist, I would log into Jupyter Hub, supply my OpenShift credentials, and choose the image and the resource size, and I'd likely choose 1 or 2 GPUs to allocate my job to speed up my model training effort. To save time, I've done that already, and this is my Jupyter notebook that I, as a data scientists might use to train my model. We're going to briefly walk through its output again. A point to re-emphasize here, our purpose is not to showcase the data science, rather the capability that OpenShift brings on the tools for data science. So you can see here that we're using a random forest classifier algorithm. For those of you who are data scientists, you'll know what a random forest classifier is. For those of you who aren't, it's a popular algorithm in classification type scenarios like fraud or not fraud. The important point here is data scientists can pull in and use their chosen tools, their chosen algorithms. Next, they enable a confusion matrix. Again, for those of you who are not data scientists, a confusion matrix is a nice, easy way to visualize correct and incorrect predictions against a binary classification like fraud or not fraud. Next, we're going to choose from where we pull our data. We can choose from a CSV file, which is what we'll do, perhaps from a Spark cluster, or from a virtual database, or from any number of other sources we could pull our data from. Now we define a few functions that pull in the data from our chosen location, and at this point we're going to output the column names or tunables here, with which we can train the model. Next, we actually start the training of the model, and we make an initial attempt to create the model, and you can see our model accuracy here on our first pass is 85.2%, which is pretty good. We can also visually assess how we did on our confusion matrix. You can see these dark quadrants showing the incorrect predictions of fraud and not fraud. So they're still a little high, and these two are the incorrect ones on our second data set. We can also, at this point, make the decision we want to improve our model. So now we can output the columns here that are relevant. The more over to the left, the more they correlate to fraud, and these ones here are much less relevant to fraud or not fraud. And we can also output, use our correlation analysis, those columns that are relevant. Now what we do is we're going to recreate the model, discarding the unimportant features and only using the important ones. And you can see our model accuracy has jumped up to 97%. And our confusion matrix also reflects this. Our incorrect predictions are down to 0 in one data set and almost 0 in the other. Now we test our model, output some data, and the final thing that we do here, so right now as a data scientist I'm now happy with my model. So finally we define a utility method here, this predict method, which is gonna expose our model using the runtime model serving component Selden, which is two of model serving components that feature in our demo. Again, highlighting OpenShift's flexibility. Alright, so at this point I'm going to switch across to another browser, and this time I'm logged in as a data scientist as well. And I'm going to highlight two more data science focused Jupyter notebooks. Again, the focus here is not on the actual data science, rather an illustration of the freedom offered by the OpenShift platform using different tools, again all available self-service. And in this model we're also training, this notebook we're also training a model. So we're going to use different libraries, Keras here, which is the user-friendly wrapper around the lower level TensorFlow APIs. And we're going to use TensorBoard here for visualization. Yeah, I'm going to highlight that important factor. Again, we're not going to dwell too much here. We define some functions for pulling in our data. We actually pull in our data from our object store that the data engineer pushed to previously. We split up our data, define the model using the Keras libraries, compile, train the model. And this time we use 10 epochs, or model training runs that are applied by the machine learning algorithm. Next, what we do is we upload our model to our visualization server, and we also upload it to our API server here, which is TensorFlow serving. This section addresses a common pain point in AI/ML: how to share and move models once the data scientist has done their training. So in this demo, we showcase two possible ways this challenge can be addressed. First, in this way here, directly saving it to our component TensorFlow serving. And this simple line of code makes it accessible over an API to client applications. And our second approach that you'll see shortly is as a continuous integration and continuous delivery pipeline. So now what we're going to do is focus in on the third data science focused Jupyter Notebook. And we'll showcase this very briefly. Again, as it touches on a very common data science activity, which you can see is hyperparameter tuning. And again, it highlights the critical element that OpenShift facilitates, which is visualization tools, also TensorBoard here. Again, the focus is more on the breadth of our capability rather than on the actual data science. So you can see here, we're pulling in our hparams, hyperparameters library. We define some functions again for pulling in our data. We pull in our data from our S3. Now we define our hyperparameters. Discussion on hyperparameters is really out of scope right here, but suffice to say, they're used to add robustness to our model training effort. And we define three of them here, which are num units, dropout, and optimizer. Next, we actually train the model, and we loop through various values for various combinations of values for our three hyperparameters: num units, dropout, and optimizer. And with each pass, we're also pushing data to our visualization server TensorBoard. And here we output some data here, but at this point I'd like to highlight TensorBoard, the visualization tool. So you'll recall the last two data science focused Jupyter Notebooks push data to a visualization server TensorBoard. Here, this is one with the 10 epochs, and you can see some useful data here for the data scientists that sort of display them cumulatively, or you can drill into individual ones here. And secondly, the last data science focused Jupyter Notebook, the one where we did our hyperparameter training, our various combinations of the three hyperparameters: num units, dropout, and optimizer, and the associated accuracy of each. So this nice tabular view makes it very easy for the data scientist to visualize and assess their accuracy as they go, as they train, and as they experiment. So that's really the data scientist focus part of the demo. So now let's switch back to our slides again. And the next part of our demo covers an area that Red Hat and OpenShift have developed a lot of capability in over the last few years. That is DevOps and its intersection with AI/ML, so-called ML Ops. So in this demo, we automate a continuous integration and continuous delivery pipeline flow from the point in time that the data scientist is happy with the model and pushes their model code into source control. Obviously, source control being a repository for Jupyter Notebooks and other source code. So in our demo, they check their code into source control, represented by this Git icon here. And the CI/CD flow is implemented by Tecton, represented by this icon. And the pipeline showcases three things. First, a model accuracy check, enforcing quality control. So if the model is less accurate than our pre-configured minimum, say 85%, the pipeline will fail and it'll never reach production. Second, container security, where we build a container image housing our model, then we scan it for vulnerabilities. If any are found, it'll never reach production. And third, speed. The automated nature of the pipeline means it can take just minutes to reach production. So MLOps addresses challenges that are experienced by various stakeholders in the AI/ML workflow, including for IT ops, provides a smooth, automated, and therefore less error-prone flow of work to production in a safe, quality-assured, and rapid fashion. This is often a huge challenge that's easily addressed by OpenShift. For data scientists themselves, it also alleviates common challenges, that is sharing their models, moving them to production. And obviously for application developers, they need high quality and secure models with which to add value to their apps and make them more intelligent. So let's switch across to OpenShift. And you can see here 3 pipeline runs that I've done previously. The first 2 failed and the third succeeded. I'll get to those in a moment, but first I want to highlight a webhook, or a trigger if you will, that fires up a pipeline run and enforces all the checks that I just mentioned whenever the data scientist checks in their model into source control. Checking in being effectively like submission of their work to the system when they're finished training and they want to run the security and quality checks and share it with others. So this is a source file here, and I can check in my code just by clicking here. Checking in will now trigger a pipeline run. So if I switch back to my pipeline runs, you can see I had 3 previously, and that act of committing or checking in just a few seconds ago triggered the pipeline run. This ensures that quality and security are constantly enforced. So let's drill now into our pipeline runs. The first failing run. So what does the pipeline do? First, checks out the code, extracts and trains the model, similar to what happened in the first Jupyter Notebook run. And the first check that it does is it validates the model accuracy against a pre-configured minimum level of accuracy that we insist on, say 85%. Didn't meet that minimum, as was the case here. It fails and it never gets to production. This validation check also allows what some organizations consider best practice, that a different data set other than the training data that the data scientist had access to is used to validate the model. So this workflow really enables this type of check and best practice. So now we can drill into our second pipeline run. You can see that with this pipeline run, we fixed our model accuracy issue. And the next thing that happened was OpenShift built a container image, housed our model, and then started to scan the container image for vulnerabilities. And you can see that a known vulnerability was found due to an old library that was in one of that was imported into that container image, and the pipeline failed. So finally, our third pipeline run here, you can see that we fixed our vulnerability by updating the version of the library to a newer one, and finally the deployment happened. At this stage, what the pipeline could do is deploy our model into say a pre-production or a staging environment, for example, or it can push it all the way to production. So that's really the MLOps portion of the demo. Now what we're going to do is we're going to switch back to our slides here. And finally, in our demo, we need an effective way to consume our model at runtime, effectively the inferencing stage. So who does OpenShift add value to at this stage? Well, there are 2 main beneficiaries. First, application development. Who need an easy way to consume the model, consume the latest trained models. And secondly, lines of business who are responsible for the delivery of intelligent and often what we call hyper-personalized applications to customers. And OpenShift provides an easy way to add this extra value that's brought about by AIML. So you recall earlier that each credit card transaction, when it's routed to the payment service, is routed across to our fraud detection service, along with the details associated with that particular transaction. And then it's sent across to one of our model serving components for inference, either TensorFlow serving or Selden. In our demo, we're going to use TensorFlow serving. So now we're going to switch across to our API testing tool. In reality, you can see here this predict method. In reality, this would be an intelligent application, but for our purposes, demonstrating a simple API call Postman is good for that. You can see we're going to hit our TensorFlow serving component here for inference, and we also send in various masked numerical representations of actual factors that are relevant, whether it's a fraud or not. Things like the size, type of transaction, location, dollar value, balance, etc. And these are all passed into our model. And when we make that API call, you can see that it returns back with this particular transaction a very low probability of fraud, less than 0.5%. So that's really the end of the model serving component of the demo, and indeed the demo as a whole. Thanks for watching.